10:30, but today I am having a deadline at the noontime, but I don't want to skip the course, so I want to come and then just start the lecture, and we have videotape. If later on there is someone who missed the beginning, don't worry, we have videos. Okay, so last time, today I'm going to be very quick because I need to meet some deadline. So this is what we have learned last time. We have this maximum strain energy model and maximum shear stress model. Shear stress model is the small one, more conservative. Strain energy model is the largest one. Okay, depends on your Poisson's ratio. Different Poisson's ratio give you different margin. Now, today we are talking about a new model. It's a new term called distortion energy. You probably have never heard of distortion energy in the past. In your solid mechanics course, mechanics of material course, you don't hear about distortion energy, maybe never. So let me tell you what is distortion energy, and based on that, we can derive a new equation, and we're going to use it for our design equation. So here's a general configuration of an element being pulled along three directions and being stretched along three directions. We have delta x, delta y, and delta z. Now imagine this deformation includes a total volume change and something called distortion. So what does that mean? It's like you have 100% of your material, and after applying the force, let's say in the volume, it is enlarged by 10%. So you have 10% of volume increment, right? Now, if I can focus on the 10% and say, hey, let's think about, let's just distribute the 10% of volume increment everywhere. So this is basically pure volume change. So it's like a 10% increment evenly applied everywhere. So it's like no matter what kind of force we apply, there are certain percent of the forces inside the force that we have that contributes to the pure volume change. So allowing this structure being enlarged by 10%. After that, you are going to change its shape. It's like playing the clay, like a deforming, but deforming it without changing the volume anymore. So distortion is like a deformation without changing the volume. Okay? So it's kind of like separating two effects from the general effect, separating them. So one portion is like a pure volume change. The other portion is about change of shape without volume change. So that part is called distortion. And if you agree with this kind of separation, we already know strain energy per unit volume from last time, from the strain energy model. And this time we are going to talk about this guy, the strain energy for pure volume change. This could be computed. So if we are able to compute strain energy for pure volume change, then U minus UV give us distortion energy. So there's a trick. we're going to compute distortion energy by U minus UV. So we want to study the pure deformation without volume change part. And let's take a look how that amount equals to. And then we're going to figure out how that amount should be limited by. So figure out the limit of that part to form a new equation based on that concept. And we will then figure out how that equation differs from what we had earlier. And let me tell you the conclusion. Pure deformation without volume change has nothing to do with Poisson's ratio. So inside this part, no Poisson's ratio. So what's interesting is that the Poisson's ratio part is only existing in here. Also in strain energy. But once you separate the pure volume change part, over here there's no Poisson's ratio. So we are able to form a new equation that doesn't require value of Poisson's ratio. Okay, so this model is the most common model that we use nowadays. Okay? So if you follow what I am talking about right now, so first we will be focusing on strain energy for pure volume change. If you don't understand this part or you don't believe it, that's also fine, because later on it's just a one design equation. So now, let's talk about how the stress could be separated into two parts. Because earlier we have the pure volume change, the first part right here. Since they are deforming in the same way along all directions, so the stress along each direction should be the same so that they can expand evenly. Okay, but we just don't know what's the value of SV. We just only know they should be the same, so this pure volume change can be enlarged evenly. So that's the only thing we know. There's a value, stress V, SV, right there. So since in the earlier page, the left part equals to the first plus the second part. So every stress value in the general strain energy part equals to the stresses along all three directions that contributes to pure volume change plus whatever that's left, the residual of the equation. So over here, these are the stress for volume change. Okay? And the prime one would be the stress for distortion. Okay? So, even when we separate them into two parts, all the Hooke's laws we're still in the elastic material region. All the stresses still follow Hooke's law. So all the terms about Hooke's law are still valid. Okay, so we are formulating the Hooke's law for the distortion stress, the stress of distortion part. Okay, so this is how we come up with these. And there's a very important assumption, which is right here. In the previous page, we said for the distortion part, there's no volume change. So what's the equation that represents zero volume change? That equation is going to be defined as the sum of the strain along all three directions equals to 0. So it's like here I could have plus 1% of increment, but right here I need to have minus 1%. So totally 0% of volume change. So this is how this concept of zero volume change could be mathematically described. And that's an assumption. Okay? So once you have this, you can plug in all the Hooke's law equations into here. You come up with a new equation right here. Okay? And since we know the Poisson's ratio cannot be 0.5, it has to be smaller than 0.5. So it won't be 0.5. And this term won't be 0. If that term won't be 0, so right here, whatever you have right here has to be 0. So it turns out the sum of the stresses for distortion equals to 0. That's a new equation that we come up with if we agree with this assumption. So over there, I can plug everything back to what we have here. It turns out we end up with this new equation. If you have this 3 equation and integrate it with this new equation, we end up with this. At the end, the stress for pure volume change is the average of the stresses along all 3 directions. At the end, it turns out the equation looks like that. Okay? So now we figure out a way to find out the stress for pure volume change. We don't know the stress for distortion. We only know the sum of them equals to 0, but we don't know the value of each one of them. Now, based on these, we can compute for SV. Okay, so these are the SV. And of course, later on, if you have the general stress minus SV, you can compute for the stress for distortion. Okay? So once we have that, what can we do? We can now try to study for the strength energy for pure volume change. So let's do that. This is the general stress equation, but you plug in the volume change part here. So you come up with the expression of all the stresses for distortion. The prime represents the stresses for distortion. And over here, you realize all the stresses for distortion can be described in terms of the principal stresses along all 3 directions. Okay, and also the strength energy for volume change can be computed by the strength energy, so basically stress times strain, for each direction, right? And you know, for volume change, the strength energy is the same along all 3 directions. That's why I multiply by 3. Okay, that's why you have a 3 here. Okay? So that would be the strength energy for total volume, the volume change along all 3 directions. So at the end, you have this 3/2 times the SV and the strength V, and this is from Hooke's law. Even its strength for volume change is still, the Hooke's law is still valid. So you can plug in the Hooke's law. Okay, so organizing the terms, you end up with a new equation like this. And you already know the value of the SV. You plug in the SV, so you end up with a new equation right here. Okay, and this is after reorganizing all the terms. So the strength energy for pure volume change ends up with this equation. So over here, you do have the Poisson's ratios term, and you do have the principal stresses along all 3 directions. So you have this. So why do we compute for this? Like I said, we actually want to compute for distortion energy. So how do you compute for distortion energy? You use U minus UV to compute for the strain energy for distortion energy. So U, this is distortion energy, equals to the strain energy minus the strain energy for volume change. And the first term came from the last lecture. The second term came from the last page. So all you need to do next is to just do some math, reorganizing all the terms. You end up with something like this. Okay? So over here, what's the key about this equation? We are going to go through the tensile test concept again. So for strain energy, and not strain, distortion energy. Let's see what would be the distortion energy when you are doing tensile test. So earlier we have this tensile test Mohr circle, and here is stress, here is shear stress, here is your principal stress, right? So you can, in here is Sx. So all the rest of the terms goes to 0 for tensile test. So this would be the distortion energy when you are doing tensile test. What's the limit of it? When this equals to the yielding strength, that would be the limit. So what's the limit for this value? The limit for this value equals to whenever Sx equals to the yielding strength. So that would be the limit. So now we know the distortion energy has a limit. So this is the limit for distortion. Okay? So we just put them together. Very important term right here. When we put them together, this is distortion energy has a limit. And all the Poisson's ratio terms, the coefficient terms, the Young's module terms can be eliminated because they are the same on both sides of the equation. So it ends up with this new equation. Okay? And there's a name for it. Usually there's a name. It is important, right? Whatever on the left-hand side is called von Mises stress. Okay? So what is von Mises stress? It's a kind of equivalent stress that covers the stress condition in all three directions. All directions. Think about it. If you perform Mohr circle analysis and realize what's the value for the principal stresses in all three directions, and you put them together in this form, it ends up with a new stress term called von Mises stress that has no direction. It's like a stress value. Okay, and because of the way you form this, it's usually a positive value. So it's always positive. Okay? So this positive von Mises stress value represent the stress level that a material is carrying. And in finite element analysis softwares, the numerical softwares, you can actually ask the software to show you the von Mises stress. So whenever you do that, you usually see an element that has a different color distributions, they're red and blue. Usually red represent high values of stress. And from the color bar, you do see some stress values, but there's no direction because they are these are equivalent stress level representing no direction. It represents the stress level from all directions. Okay, and because it has no direction, so it's very good for design. We don't care what's the stress. The stress has no direction. It's like under how the material is under a certain amount of pressure. And that value has to be smaller than yielding strength. I don't know why someone is keep on calling me, but I'm gonna finish this. So this one is a general equation, and here is the special case for plane stress problem. Okay, and for that plane stress equation, if you make a drawing of it, at the end, it's actually the ellipse highlighted in blue color, this one. So that is the maximum distortion energy model, and it has nothing to do with Poisson's ratio, and it passed through this corner point. Okay? And so how do you memorize it? Or how to recognize it? If you apply 0.5 here, which is the Poisson's ratio value, that won't be happening, but if you just plug in right here, you end up with this equation. Okay, so it's like if you are studying maximum strain energy model, you won't have 0.5, you have a Poisson's ratio that is lower. You will end up with a design boundary that is having a margin a little bit far away from the blue region. But if you just consider the distortion energy model, it's just like plugging in the ideal Poisson's ratio value to this particular equation. You end up with something the same equation, but over here the coefficient equals to 1. So that would be the smallest possible ellipse that this figure can take, and it covers the dashed line area and still allowing some safe margin at those round areas. Okay? Let me just answer this. Okay, I'm sorry, super busy today, but I'm finished. Basically, it's a more conservative safety region, and if you apply safety factor right here, it's gonna be a smaller region. Okay, that's it. That's everything I want to cover today. So the conclusion is, you don't need to worry about how I derive it. Just the only thing you're going to use is this guy. So later on, I will ask you, hey, solve this problem by maximum distortion energy model with the consideration of safety factor. And there's an equation list. This equation will show up somewhere, but I won't tell you which one is which one. So you need to recognize, this one is the one. Don't plug in the wrong one. That's it. Okay? So I'm sorry, someone is waiting for me, and also a deadline is waiting for me. Is it okay I just finish for the day? Let me also check about tomorrow. What's the lecture schedule for tomorrow? Tomorrow is still static loads. So tomorrow I can show you some problems, how we solve it. Okay? So Ella, please do the attendance check. Okay, once you are done, you can go. quietly. Thank you. Bye bye.
Sorry.这边。